meeting is being recorded.
Ringraziare Ivan e Giacomo per avermi invitato a parlare.
Wait a second, Paul. Wait a second, Paul. I should introduce you. I'm sorry.
Okay, well, I've
Okay.
been waiting a little bit.
So thank you everyone for joining today to this new episode of Ithaca. And today, the first speaker of the day is going to be Paul Taylor, and the title of the talk is A Categorical Replacement for Replacement. And Taylor, take the stage. Paul, take the stage. Sorry.
Thank you very much. Okay, so we have toposes give us a partial version of the supposedly official foundations of mathematics, but there's long been a bit missing. So questions are, do we actually need it? And how can we express it in native language of category theory without parroting set theory? But I will take and generalize some basic set theoretic ideas in doing this. So why do we need it? Well, there's some inessential uses of replacement. If you have a functor into sets from a small category, well, it's a tiny bit difficult to understand what that means. But anyway, we can turn that into a discrete vibration with small categories. And then we could do set theory, we could do sheaf theory just with those small categories. On the other hand, we're going to need some set index colimits of sets, whatever that means. And that pre-sheaf of sets is the basic construction that's part of that. Now, what are the inessential uses of replacement? Sorry, the essential uses. Well, one is that in various subjects we get infinitely or transfinitely iterated functors, especially in homological algebra, and more complicated things in proof theory. So we have a magic construction category theory called gluing that proves consistency and normalization and so on. If you know of other examples, please tell me them privately. So the canonical example that comes from set theory is the von Neumann hierarchy, and in particular at stage omega 2, this is something that provides an elementary topos, but is not definable in elementary topos theory. So we want to understand what this is about. Now, I'm not going to construct the transfinite iterations of functions from my proposal today. That's partly because I haven't worked it out yet. So I'll give a lecture sometime in the future about that. Today, I'm just going to explain what my proposal is, and also how to use Zermelo-Fraenkel set theory, which I don't think I'd ever understood before working this out this year. I don't know whether you know of any accounts of this in category theory or algebra textbooks that tell you how to do it. But let me assure you that we're going to do category theory and not set theory in the lecture. So in the von Neumann hierarchy, and particularly the case that I mentioned, we have some big unions. So it's tempting to think that replacement is about having big unions. But what I claim is that we also need to understand the diagram of which we're going to take the union. How these, so for example, in V omega 2, we have to understand this system of iterations of the power set functor that we can't do in one go in an elementary topos. So what do I mean by the native language of category theory? Well, of course, adjunctions are surely the most important part of category theory. So all the connectives we use are defined by universal properties. And I think of this as being a different notation for type theory. So any adjunction is equivalent to a system of introduction, elimination, beta and eta, and various other rules in type theory. So what type theorists do in building their theories is that they start off with the most simple things, and they assert new rules for introduction, for example, of lambda terms in this example here, and that's what we do in defining a topos or some other categorical structure corresponding to a type theory. We assert that some simple functor have an adjoint. Now, okay, so if we're going to ask whether functors can have adjoints, there is a classical supposed answer to this, namely the general adjoint functor theorem, which I think is due to Peter Freud in his thesis. Now, I strongly suspect that this doesn't have any. Isn't actually of any use. So there's an example from group theory. If you want to construct free group on a set using some version of the general adjoint functor theorem, well, okay, the example involved projective linear groups on of dimension 2 of arbitrary fields, of which there are whatever many according to your cardinality. So I'd like to know, are there any uses of the general adjoint functor theorem where we can't just as easily describe the adjoint? Okay, well, if a functor is going to have an adjoint, it has to preserve colimits, and so the relevant colimits are going to exist in the category. So we need to talk about set index colimits, and we're going to assume, so the principle I'm going to describe is not very interesting if you just apply it to sets. We don't want to apply it to other categories like posets. And we're going to assume that the category in which we're working creates colimits over sets. What we need to do is to know how objects are described as colimits in some sense of simpler ones. And I claim that finding the diagram is the issue. Okay, so how do you construct colimits in sets using replacements? Well, this functor into sets is actually precisely the data that is needed for an instance of the axiom of replacement. So the way that set theory is officially defined is as a first order untyped theory with these predicates ranging over the universe. So we have some functional relation with some variable x that for each x produces a unique y, which could be any set in the universe. We don't know how it produces. We don't need to say how it produces it. It's just so long as the predicate says what it is. And replacement says that you can form the image under this functional relation of any set. And that's exactly what we need to do in order to turn a functor from a small category into sets into a presheaf over that. And there's a bit of messing around to do, which is easy category theory. I just want to emphasize the way that we're using replacement to do this. Okay, now as I said, we're going to we build up a type theory, and in particular our proposal for replacement, by asserting that some functor has an adjoint. We need to say where these come from. Now, in the case of the exponential, I said, it's sort of easy that this thing is going to have an adjoint, and you have possibly some explicit way of constructing it. But the interesting situation is where you're going to have to construct the adjoint using recursion. So the type theoretic rule for doing that kind of thing would have a term of the new type as a premise in the introduction rule. And an example of that is adding an element to an existing list, which is not a very powerful example of a functor requiring adjoints, but more powerful things like that is what we want to be able to do. But if you have anything that requires recursion, anybody who's run a program knows that it might not terminate. If you strengthen your logic, it might lead to a contradiction. Well, that's why things are interesting. So somehow we have to deal with the possibility of non-termination. So the traditional way of doing that is something called well-foundedness, which has many classical definitions that I'm sure you all know. I'm going to give you the categorical one, which you probably know from me as well. And so the general plan is that we're going to, we're going too fast, right? The general plan is that we're going to work in a category of well-founded structures, and we're going to have a full replete subcategory of that. And we're going to ask that this replete subcategory have a reflection. So you might naively think that reflecting into a subcategory might be tamer than the general situation of asking for an adjoint, but that's certainly not the case. And the way we define our subcategory is by means of a generalization of the axiom of extensionality, which you might naively think to be the most innocent of the Zermelo axioms. But no, that's not the case either. And I believe that set theorists have been aware of the power of extensionality for a while, though I don't know the details of that. Okay, so let's be more specific about this. We're going to work with well-founded coalgebras. And the useful thing about those is that they're approximations to the initial algebra for the same functor. And the interesting thing is that well-founded coalgebras can exist when there is no initial algebra. And the leading example of this is the covariant power set functor, which has no initial algebra because it has no fixed points. And a coalgebra for this functor is a binary relation. So this idea was first exploited by Gerhard Osius in his reconstruction of set theory from an elementary topos in the mid-70s. Okay, so here's the definition of a well-founded coalgebra. It's one such that any subobject U, if we form this pullback, the functor applied to U, and that factors through U, well, that's diagram is expressing the premise of the induction scheme. Then we want to say that U is the whole object, and it's not very difficult to, in the case of the power set functor, it's not difficult to see that is the same, is the familiar intuitionistic induction scheme. And similarly, recursion, which is what Osius used instead of well-foundedness in his categorical set theory. Well, we have this 3 equals 1 diagram. And unfortunately, in Osius's paper, there was the obvious misprint in this diagram. Okay, so if we have a well-founded coalgebra, it has a unique coalgebra to algebra homomorphism to any algebra. And the proof is in this paper of mine called Well-Founded Coalgebras and Recursion. And next to it, slides are going to sketch the general idiom of this. Firstly, the idea came from von Neumann's recursion theorem, which appeared first in his 1923 paper called Introduction to Ordinals, which is translated in the Van Heijenoort volume, and then reappeared in a longer 1928 paper, which is only in German, so I don't unfortunately have that one. And the idea of it is that it successively considers attempts at solutions to the recursion equation, starting with the empty one, and the successor stage. We start with the subobject B, and there's a construction of the successor subobject SB, which is obtained using this pullback. And the point is that a coalgebra is well founded if and only if this successor operation has a unique fixed point, namely A itself. So this corresponds to the diagram I had earlier, but in the simpler case of just a pullback instead of a broken pullback. And we also need this thing to be well powered. That is to say, the sub-coalgebras are indexed by a set or object of the topos. This can be formalized using index category theory. Okay, so the situation is that the system of subalgebras of a well-founded coalgebra has at least one. It has directed unions. It has an inflationary monotone endo function, and any fixed point is the whole thing. And that is enough, based on the idea of Vito Pataraya, which I've developed somewhat, and with not an ordinal in sight, that is enough to deduce a greatest element of this system and an induction scheme for proving something about the greatest element. Now, in the basic results in this theorem, the predicate on which we can do induction is definable in the logical topos or bounded Zermelo set theory. However, when we come to the main theorem about the existence of adjoints, we need to perform induction using a predicate that involves unbounded qualification, that is to say, over the whole universe. Right, now then turn to extensionality. So here is the familiar extensionality rule from Zermelo set theory. That's equivalent to saying that the structure map of the coalgebra is 1-to-1 in set theory. So we're going to generalize that to arbitrary functors, and we say, well, firstly we say that this structure map is going to be mono in the category, and we'll come on to further generalizations on the next slide. So the initial algebra is well founded and it's extensional as well. When we tighten up the notion of extensionality on the next slide, the initial algebra is still extensional because the structure map is an isomorphism, as you know. Okay, so we're going. This is the principal innovation in this piece of work. That instead of just an ordinary mono in the standard categorical sense, we're going to have the M maps of a factorization system. I hope you know what a factorization system is. It has two classes of maps called E and M, and they're orthogonal, and all maps in this sense of this diagram, and every map factorizes as an E followed by an M. and we need the functor to preserve n maps and really well-behaved directed unions as well. Now, well-founded extensional coalgebras have some quite remarkable properties. They behave just like sets, even though we haven't said anything about what the functor is. It doesn't have to be the power set. We've generalized the notion of extensionality, should we say, through the roof up to the sky. But even so, this category has some remarkable properties that's very similar to the universe of sets. Well, it's a pre-order. There's at most one homomorphism between the two objects. This homomorphism is in the class M. There are directed unions. There's a binary intersection operation, which it's not a simple thing by any means. It's constructed recursively by the same sort of method as the recursion theorem from well-founded coalgebras to algebras. And then if the underlying category has well-behaved colonnades like category of sets does, then it has overlapping unions, just like those that strange things that we have in set theory. Though we're not going to use those. So these properties of set-theoretic union and intersections and so on, which are very weird when if you see them as a categorist in set theory, actually naturally arise in the category of extensional well-founded things, despite our significant generalization of those. So why do I want to use and do this major generalization from ordinary monos to epis and monos to factorization systems? Well, it's because the interesting thing about replacement is it builds skyscrapers. So what we imagine is that the M maps are inclusions that have to be closed under rich structure. So the simplest example to think of is that plump ordinals are coalgebras for the downset functor in posets, and being downsets, well, this is rich structure that they have to be. But those are what the end maps have to be. And since there's this Galois connection, contravariant Galois connection between E and N maps in a factorization system, we're saying that to beat an E map doesn't have to be anything like surjective. There only need to be a few generators, and then you get an enormous structure. This is probably the same idea as dilators, or at least the name suggests so, and the category theory of them suggests so. But as yet, I don't understand how proof theories use them, and I don't know what the definition, depending on ordinals, is going to be highly classical. So that needs to be rethought very thoroughly. Right, so that's why we're doing it. Now, okay, so what we're going to our replacement for replacement is going to be that the full subcategory of extensional coalgebras in the category of well-founded coalgebras is reflective. So any well-founded coalgebra A is to have an extensional reflection. Now, E being the extensional reflection has a structure map that's in M, formerly a mono, and well, the what is it? The unit of this adjunction from A to E. Well, in a priori, it's just a homomorphism, but in fact, it has to be in E. Why? Because if it was some general homomorphism F, we could factorize that as an E followed by an M, through some intermediate coalgebra E primed, and it's easy to show that that's extensional too, and therefore by the universal property, there's the comparison map M. The map between M between them is an isomorphism. So that's fairly easy. What's not trivial is that this is sufficient, and this makes serious use of a result which I'm afraid is not in the well-founded coalgebras and recursion paper, but I did prove it yesterday morning. So it is true. So there's as I said, extensional well-founded coalgebras have an intersection operation similar to the one in set theory, which has to be constructed recursively. Well, that's an intersection with respect to other extensional well-founded coalgebras. In fact, this thing has the property of a product in the larger category of well-founded coalgebras. That is to say, we have some other map from a well-founded coalgebra that goes to both E and F, then it factors through E intersect F. Not trivial, but it is true. Okay, so we have this fairly simple situation that the extensional reflection is an epi going to an algebra, a coalgebra which has a mono as its structure map. We can simplify this a bit. The extensional reflection is an E homomorphism, but because of the observation we made in the previous slide, for the question of existence, it suffices that be any homomorphism to an extensional coalgebra. And that's useful because if A has one of these, then so does TA, because T preserves M maps. And also, if any subcoalgebra of A has one, then so does its successor, SB, because SB has a map to TB, which, as by the previous remark, has a map to an extensional coalgebra. Okay, so this is an extensional predicate on the object of predicate whose subject is a well-founded coalgebra, and the predicate is that there exists a homomorphism to an extensional coalgebra, and that's not something we can say within the topos. It's quantifying over the whole universe of things in the category. So it's an unbounded predicate. So this is when I was doing this, I began to understand the difference between Zermelo set theory, which allows these unbounded predicates, and the language of a topos, which only allows bounded predicates. Okay, so we're coming to the induction. How are we doing for time? We're not doing too badly for time. Right, so we put these ideas together. So we want to prove, on the basis of what we've done previously, that any well-founded coalgebra has an extensional reflection with respect to any factorization system. Well, we're assuming that the thing is well powered. That is to say, it has only a set of some objects. These form a DCPO because we've provided colimits. It has a least element, and we've defined an inflationary monotone successor. then we have an unbounded predicate, as we've said, so we're working in Z of, not in an elementary topos. The empty set has an extensional reflection. The successor preserves this property, and so do directed unions. And therefore, by my version of Categorical theorem, the predicate holds of the greatest sub-coalgebra, namely the coalgebra A itself. So let's recap on what colimit diagrams we've used to this. So replacement gave us set index colimits in set, as we talked about with the functors and presheaves example. But that's vague until we say what diagrams we're going to use. So that's what the question we're answering at the moment. So the well-powered hypothesis says that the sub-coalgebras, there's a set of those. So we've got this, and it has unions, and it has directed unions as well. Sorry, it has containment, and it has directed unions. And Paterai's observation says that composition gives us makes these so that in the function space of sub A, we have that's directed, and then so we have a specific diagram, namely the poset of inflationary monotone endo functions of the pre-order of the poset of sub-coalgebras of A, the specific directed diagram, and it has colimits in set given by replacement, and the argument, the simple argument we had before. These colimits are inherited by the working category by hypothesis on the category, and they're created in the various categories of coalgebras, well-founded coalgebras, extensional well-founded coalgebras, and the poset of sub-coalgebras and of endo functions of them, all by relatively simple categorical calculations. And as I said, an example of this is we take T to be the lowest set functor on the category of posets, M to be the class of lower inclusions, and E to be the class of co-final functions. Then the extensional well-founded coalgebras for this are the plump ordinals that I introduced in the 1990s. However, in the simplest non-classical case, namely classical sets on a single arrow, you can show that this grows as fast as the von Neumann hierarchy does, and it's too big to be defined within the elementary topos, and therefore we need this construction for that to exist in ZF. And I hope I've more or less stayed within my time. I think I have. I'm still working on how to do constructions like transfinite iteration of functors, and we'll talk about those on some future occasion. I apologize for hurrying through this without allowing interruptions, and I know that it's difficult stuff. So I'm going to repeat this lecture on Friday in our local seminar in Birmingham, which will also be online. So see seminars.org for the Zoom details for that. You can find my papers and slides on my webpage, and I've been down a lot of historical rabbit holes doing this subject. and on the way I've translated various papers, and you'll find those also on my webpage. Thank you very much for your attention.
So thank you very much, Paul, for your very nice talk. And now, before thanking you one last time, we move to question time because we still have 5 minutes. So we definitely have time for a couple of questions. If someone wants to ask a question, please unmute yourself and just ask it.
Carlo has a question. Hi, Paul. Thanks for the talk. I know that Joyal and Murdyke have a definition of what they call a class category, which is a category equipped with a class of small maps.
Yes.
The axiom of replacement, the closure under this class of small maps under composition. So I wanted to ask your categorical form of replacement matches up with their categorical form of replacement.
Well, I think that the replacement is simply built into their system without really recognizing what it's doing. That's not meant to be a disrespect to them, but it doesn't seem. So I think what's difficult to understand about this subject is obviously we need some big unions, but there's something special going on about how we formulate the big diagrams of which you're forming the unions. And I think that's the question that I've addressed that is not addressed in algebraic set theory.
Okay, cool, interesting.
I'm being trying not to assert too much because this is, it's taken me a long time to get my head around this, and I need somebody else to have, to argue these things out, to pick me up by the scruff of my neck and argue with me about this.